The focus is on all the problematic questions. So we will start with the question 5. Question 5 says, which moving object has a resultant force acting on it? So you must understand what is a resultant force and its implication. When we're talking about resultant force, we are saying that resultant force is equal to mass times acceleration. That's the resultant force, mass times acceleration. So if we have a resultant force, there must also be an acceleration. And if there's an acceleration, then the speed or velocity is not a constant. So we only have to look for the situations where an object does not have a speed and velocity that is not a constant. So I have circled the correct answer, so I will show why the wrong answers are wrong. A diver rising vertically through water at constant speed. The fact that speed is constant means that the resultant force is acceleration is 0. A train going up a straight incline at constant speed, again constant speed, means that the acceleration is 0. A parachutist descending vertically at terminal velocity, again terminal velocity, that's constant speed, constant velocity, acceleration is 0. So all three are wrong. Then B, why is B correct? An aircraft circling an airport at constant speed. The fact that it is circling, even though the speed is constant, but it is circling, it is moving around in a circle, then its direction is changing. And velocity being a vector quantity, when direction changes as you are moving in a circle, velocity is changing. So there is an acceleration for B. The next question is question 7. A sphere collides head-on with a second identical sphere y, which is stationary. The mass of each sphere is 0.15 kgs. Sphere x is traveling with a velocity of 2 meters per second before collision and provides an impulse of 0.21 Newton second on sphere y. What is the velocity of sphere x after collision? So when a question comes like this, we automatically know that they are implying to the principle of conservation of momentum. Okay, so we have sphere x before collision moving with a speed of 2. That's sphere x. Then sphere y, we are told that it is stationary at first. Then after collision, we have a sphere x, and then we don't know its speed. We are going to look for the speed of sphere x. Let's just call that sphere A. Then sphere y, we don't know much except that it has experienced the impulse. Now you must know what is impulse. Impulse is force times time on sphere y, which is the change of momentum of sphere y. Right? So now we're going to apply the principle of conservation of momentum. What does it say? Let us apply it. For sphere x, I'm going to consider it to be sphere 1. This is sphere 2. This is sphere 1. This is sphere 2. So I'm going to say that the total momentum before collision is supposed to be m of sphere x, which is m1, times u1, its initial speed, plus m2 for sphere y times its initial speed, which is equals to the momentum of sphere 1 finally plus the momentum of sphere 2 finally, like that. So knowing this, then we substitute now. What are we given? We are given the impulse on sphere y. So in other words, we are given the change in momentum of sphere y, which is sphere 2 in my question there. So if you check this out, we can actually say m1 u1 is equals to m1 v1 plus m2 v2 minus m2 u2. I've moved this to the other side. There's a reason why I moved it, because this is the initial momentum of sphere Y. So if I move it to the other side, it comes here, whereby now it's more like a difference between the two momentums of sphere Y, the final momentum and initial momentum, which then is equal to the impulse as said by the question. So knowing this, now I can substitute values now. I can say that the mass of their masses is 0.15. The initial speed of sphere X, we're told that is 2. Then the mass again is 0.15. We are looking for the speed of sphere 1 plus the change in momentum, which is the impulse, which we're told that it's 0.21, like that. So if I take this one, will be 0.3. If I take 0.21 to the other side, it becomes minus 0.21 is 0.15 v1, which is actually 0.09, 0.15 v1. So I divide by 0.09 divided by 0.15, which ultimately is actually 0.6. So V1 is 0.6. Now if V1 is 0.6, then it has come out as a positive value. Remember, we substituted the impulse on Y like this one. So whatever the case, the impulse of Y was considered to be a positive impulse, meaning that the change in momentum of sphere Y was a positive change in momentum, meaning that the sphere Y was not changed its direction. Sphere Y maintained the positive direction, which was the direction that its sphere X was moving at first, which means that if the speed of the velocity of sphere X comes out of 0.6, then it is still going in the same direction as the direction of the speed of Y. So that's it for this question.